So as an overview about this presentation, I'm going to talk a little bit about what RFID is, some misconceptions about what are the components of an RFID system, what kind of security implications do we have, how does an RFID software stack look like, how do readers look like, how do drivers look like for RFID readers. So RFID in general, as obviously all of you will know, is a radio frequency identification used for numerous different purposes, including transportation sector, retail sector, government areas like the biometric passports. RFID is really much more a buzzword than a word specifying a particular technology. So in the world of RFID, there is hundreds of different protocols and different implementations of those protocols and so-called standards that are not really standards, but just some proprietary vendor-based schemes. So everything is, if people think of RFID protocols like internet protocols, then there's a misconception because most of the RFID systems and protocols in use are actually quite proprietary and little documented. So in an RFID system, we have a tag, sometimes also referred to as transponder, which can have specific nature. So there's very easy tags or transponders which just have a serial number that can be used as a replacement for, instead of a barcode, a European article number kind of label, stuff like that. There's write once, read many tags, which you can write once but read many times. So it's not just a fixed serial number, but a serial number that you can program yourself or whatever kind of number. There are read-write tags, which is basically like a synchronous memory card, contact-based, but not with a contact-based interface, and instead having a radio frequency interface. There are read-write tags with passive security, which means that they implement some kind of security features, cryptography, for example, access control, permission handling, and so on, but it's all implemented in a state engine, so there's no microprocessor on that device. And then last but not least, we have systems which are also called RFID, but which in reality are cryptographic smart cards with an RF interface. And the latter category, cryptographic smart cards with RF interface, is what we have in our electronic passports, for example. So RFID is basically, in the context of passports, it's just the RF interface glued to a cryptographic smart card. So it doesn't, if people talk about RFID, they mostly talk about these stupid, dumb transponders that are only, read-only, read-write, whatever kind of things. We also have readers. They're always called readers, even though they do write. It's quite interesting. Anyway, so yeah, it's like with smart cards. I've never heard somebody speak about a smart card writer. Anyway, they come in lots of different kinds of interfaces. Most of them either RS-232 or USB interface for host computers. Some of them have other protocols like RS-485. And the like. Recently, we're also seeing readers that directly hook into Ethernet as their uplink interface. Unfortunately, there are no standards and no standard APIs whatsoever. So every reader has a totally different command set. It's a totally different device, which has its different registers, its different commands, different modes of operation, and so on. This is very different from the contact-based smart card world, where now, at least for USB devices, we have the CCID standard, which is a USB vendor-independent standard for driving and talking to contact-based smart card readers. But for RFID, no such thing exists till today. The RF interface that actually exists between the transponder and the reader is also quite different in various ways. Milos is going to talk about that in more detail, so I'm going to go quickly over that. It's just important to know that there are different RFID systems using different frequencies, different modulation, different operational principle. The operational principle that we see most often is called magnetic coupling. So basically, the information interchange and the power transmission between the tag and the transponder uses a magnetic field. And it's used on frequencies such as 125 kilohertz and 13.56 megahertz. Mostly the 13.56 megahertz systems used today. Operational range is often quite small because it's a magnetic field, not an electric field. There are other operational modes or systems that can be used. One of them is backscatter. which is not really all that much deployed yet. Another operational principle works by using surface acoustic waves, and they use microwave radio signals and basically in totally different frequency bands, so it's microwave based. But the systems we usually see in today's life are all magnetic based coupling. A couple of standards, real standards as in openly documented international standards that we have in the RFID area are listed here. There's ISO 11784-785, which is used for identification of animals. So for example, here in Berlin, if you register a dog, then that dog has to have an RFID transponder implanted in case the dog is found somewhere, whatever, that the owner can be located and so on. That's what is being used here. It's very low bandwidth, 4,000 BPS, but well, how much do you need? It's just some unique number to identify the owner of the dog. There's an extension which allows you to put more data into that. It's called ISO 14223. Then there's a standard that almost nobody knows of. It's ISO 10536, which is close coupling up to 1 centimeter, which is not really very practical. I mean, if you need to be as close as 1 centimeter in order to make the device work, then you can use contact-based interfaces in most places anyway. I mean, no point on using an RF interface over the distance. Then there's currently under development the ISO 18000 series, which is quite a lot of talking going on about this right now. Sometimes in the industry usually refers to it as the Auto ID standard. Auto ID basically is intended for replacement of barcodes and these kinds of systems which we currently have for product and package labeling and these kinds of applications. The ISO 18000 series is a series of standards because it basically specifies high-level protocol operations on the foundation of a number of different low-layer protocols and on different frequency bands, different modulation schemes. So it can be used in all kinds of different technologies, from microwave to 2.4 gigahertz down to the 13 megahertz magnetic coupling. As I know, there are no real deployments of that yet, but that's what we're going to see in the future. Currently, what we see quite a lot in RFID cards is either ISO 14443 or ISO 15693. ISO 14443 has a specified operational range up to 10 centimeters. It comes in two variants called A and B. Mainly, who was A? Well, B is basically the French Postal Service's proposal or protocol, and A is, I don't know which vendor it was, but as it happens in the smart card industry quite a lot, when they get together in order to found a standard, then neither of the 2 or 3 big vendors in the field want to change any of the existing products and just want to have their existing products specified as the international standard, and then we end up with 2 different variants, A and B. Both use 13.56 megahertz, but very different parameters. There's a paper which is certainly going to be linked from the CCC homepage accompanying this presentation where there are some more details about this. The ISO 14443 specifies the physical layer, link layer. Link layer mainly means anti-collision. When we talk about anti-collision in RFID, that means we need to somehow distinguish between multiple transponders within the reach of the magnetic operational field of a device. The speed can be up to 848 kilobits per second, which is quite high. This speed is actually being used with the electronic passports in order to achieve sub 2 seconds border control timeframes, because you need to transfer, you need to do all the cryptographic handshake, and you need to transfer some 20 to 30 kilobytes of JPEG image within 2 seconds, and then you need quite high baud rates to get that job done. Especially considering the latencies that exist with these small microcontrollers. Anyway, ISO 15693 is called vicinity coupling, specified as up to 1 meter. It's like ISO 14443, operates on the same frequency band, has a two data rates, a slow data rate and a little bit faster data rate. but because they operate over such a huge distance, huge as a magnetic field over 1 meter is quite a distance, and they can only have very little power. So as to my knowledge, there are no smart, as in smart cards or any kind of cryptographic and so on, transponders available for ISO 15693, just because their power requirements of any kind of sophisticated processing would not be possible in the magnetic field over the distance. So it's mainly used for passive tags, for the stupid serial number kind of tags. So let's look a little bit closer at ISO 14443A. The anti-collision is based on a binary search algorithm, and it's using a Manchester encoding on the magnetic radio link in order to detect bit collisions. So Manchester code has this this property that in the middle of each bit clock there is a level change from either low level to high level or high level to low level. And basically, if two parties or two transponders transmit at the same time and they transmit a different signal, then you can sample at the first bit half and the second bit half. And if you have the same signal, then there must be two transponders sending, because there always needs to be a high-low or low-high transition in the Manchester encoding. So by using this kind of encoding, the reader can actually detect whether there's only one transponder transmitting a signal or multiple transponders are overlapping their signals onto each other. And bit collisions happen. So the reader can detect this by using that. So what each of these transponders have is a unique serial number, UID, PUPI, whatever. There's multiple names floating around. The reader needs to basically select a transponder. And by using a binary search algorithm over the whole, let's say it's just theoretically, let's say it's a 48-bit ID, and then you can basically, the reader says, well, you can imagine it as net masks, for example. So you can say that the reader requests a /0 net mask in all the tags which in reach will reply. If there's only one tag replying, then the reader will detect that because there's no bit collision. Every tag will transmit its serial number. Serial number needs to be unique. So if there are two tags transmitting, they have two distinct serial numbers. The two signals will overlap, will cause a bit collision, which can be detected by the reader. If the reader detects a bit collision, then it basically says, well, I want all tags with a specified prefix within the serial number, including the bit where the collision has happened, to respond. And if there were only two in the field, then only one of them would reply. And then you do a binary tree search over all the existing tags in order to select individual tags or transponders in that. And there's this looping algorithm over there. Obviously, this is one of the first possibilities for any kind of exploits or security kind of issues, because if you create a tag that causes always bit collisions at every bit position, then the reader will be unable to select any tag that exists in the field. ISO 14443B has a different bit anti-collision system. It's called a slotted alloa protocol, and it's based on a probabilistic scheme. So basically, the reader can, on its so it can define time slots, can say now time slot 1 starts, now time slot 2 starts, and so on. And every transponder, when beginning an anti-collision cycle, chooses a random number that is modular the number of time slots that the reader advertised. And just by statistic probability, it is likely that multiple tags will respond in different time slots and not in one. If they respond in one, the whole thing starts all over again. Again, we have the easy ability to interfere with this mechanism by always causing collisions and by causing retries, and getting into problems in here. So for both A and B, we can do denial of service blocker tags. They have been demonstrated. I haven't built any, we haven't built any, but it's possible to do so, and we'll certainly be able to demonstrate that at some point with some own hardware as well. Another system that is very commonly used is called MyFair. It's mainly a marketing term by Philips.